Okay, today we're going to be talking about inductance, inductive reactance, impedance. We're going to go through this whole chapter, so I'm going to try to make it as painless as possible. But first, a little background. So inductance is the opposition to current flow through an AC inductor. It's going to be called inductive reactance, and that depends on the supply frequency. Inductors and chokes are basically coils or loops of wire that are either wound around a hollow tube or wound around some magnetic material to increase their inductive value, called inductance. So this is going to be the formula that you use to find inductive reactance. It's going to be called X sub L, and that's going to equal 2 pi frequency and then your inductance in henries. So your frequency we know is measured in hertz. The numeric value of pi is 3.14. L equals inductance in henries. XL is just inductive reactance in ohms. So inductive reactance is measured in ohms, but instead of R, it is represented with an X. Alright. There's some inductive reactance factors. So the number of turns of wire, the strength of the magnetic field, the speed of the cutting action, that's going to be relative motion between the inductor and the magnetic lines of flux. The number of turns of wire and the strength of the magnetic field are determined by the physical construction of the inductor. So that's going to be size of wire, the number of turns, how close the turns are to each other, and type of core material determine the amount of inductance. And we know inductance is measured in henries. When magnetic lines of flux cut through a coil, a voltage is induced in the coil. An induced voltage is always opposite in polarity to the applied voltage. This is often referred to as a counter electromotive force. The amount of induced voltage is proportional to the rate of change of current. An inductor opposes a change of current. Okay, so we need to talk about schematic symbols. So just to show you what some of these symbols are going to look like in here. So we've got air core inductors. And they're going to be symbolized. I'm not the best of a drawer. No, we're not going to do that. Alright, so they're just going to look something like this. And then also like this. Okay? And then you've got iron core inductors. And they're going to be symbolized like this. So if they've got lines over them, they're the iron inductors. Okay? I know I'm not a good artist, so just know that the iron core have the lines above them, the air core do not. Alright. So, we need to talk about inductors connected in series. So when inductors are connected in series, the total inductance of the circuit, which is going to be L sub T, equals the sum of the inductances of the inductors, of all the inductors. So the total inductive reactance, so that's going to be X sub LT, of inductors in series are going to equal the sum of the inductive reactance for all the inductors. So the way we can represent that is, we can represent that as L sub T equals L1 plus L2 plus L3. And so that is when they're connected in series, the total inductance of the circuit equals the sum of the inductances of all of the inductors. So that's going to be your inductance total is going to equal all your inductances add together. Kind of like how we went over in DC with Ohm's law. So then if you need to know the total inductive reactance, so that would be total inductive reactance. It's going to be XL1 plus XL2 plus XL3. So just like with series circuits in DC, it's the same with series circuits in AC. So let's do an example here. Alright, so 3 inductors are connected in series. So we've got 3 inductors. And they're in series. Wow, that looks really good. Okay, so inductor 1 has an inductance of 0.6 henries. So we've got 0.6 henries. Inductor 2 has an inductance of 0.4 henries. And inductor 3 has an inductance of 0.5 henries. What is the total inductance of the circuit? So literally, all we're going to do is we're going to say 0.6H plus 0.4H plus 0.5H. We're going to add all those together, and LT is going to equal 1.5H. Okay, so it's that simple. So we know series, you're going to add them, and that's going to give you your total, right? Okay. And just to show you what it would look like drawn out, this is how it's going to look instead of how DC used to look. It's going to look something like this. So we know that now remember what the lines mean. That means it's an iron core inductor, right? Okay. So now let's do one where we need to find the total inductive reactance. Let me try to go on to the next slide, come back and see if that helps. Nope, it didn't. So I've got to keep doing this undo button. Okay. I have no idea what that does. Alright, we'll just do it over here. So we need to find total inductive reactance. So we know we can add all of our inductive reactances together and get our total, right? So if we have one inductor has 180 ohms, the next one has 240 ohms, and the next one is 320 ohms. All we have to do is add those together. And that is going to be 740 ohms because inductive reactance is measured in ohms, right? Alright. Moving on to inductors connected in parallel. So when inductors are connected in parallel, the total inductance can be found in a manner similar to finding the total resistance of a parallel circuit. If all the values of all the inductors are the same, total inductance can be found by dividing the inductance of one inductor by the total number of inductors. So that is going to be LT is going to equal L over N. Alright. Okay. Alright, so just for example, we can use the reciprocal formula like how we did in the parallel to find the resistance. You can also use that to find the inductance of a parallel circuit. So this is how your circuit would look if it's in parallel. We should all know this by now, but just as a reminder. Remember, these lines mean that it is an iron core inductor. Okay? And that's what your parallel is going to look like. So you can either do LT is going to equal 1 over L1 plus 1 over L2 plus 1 over L3. Or some people like the product over sum formula. So we know that that is LT equals L1 times L2 over L1 plus L2. So you can either use this one or this one to find inductance in a parallel circuit. Okay? So let's do an example here. We got 3 inductors and they're connected in parallel. So your first inductor has an inductance of 2.5 henries. Your second inductor has an inductance of 1.8 henries. Your third inductor has an inductance of 1.2 henries. So how are we going to get this? We need to know the total inductance of this circuit. All we're going to do, I like to use the reciprocal one. So we're going to do 1 over 2.5 plus 1 over 1.8 plus 1 over 1.2. Alright. So then we're going to come out with LT equals 1 over 1.788. And our answer is going to be 0.559 henries. Alright, easy enough. If you could see it. I hate that my head is covering it. Alright, up here it is going to be 0.559 henries. Okay, but either way, you understand that we're using the reciprocal formula, or you can use the product over sum formula. So if we was going to do that, we would just take all 3 of these, multiply them together, and then divide that on the bottom by adding them all together and then dividing by that. Okay. So we understand that. Alright, we're about to move on to reactive power. So it's measured in VARs, and that's going to stand for volts, amperes, reactive. VARs can be calculated in the same way as watts, except that inductive values are substituted for resistive values in the formulas. VARs is equal to the amount of current flowing through an inductive circuit times the voltage applied to the inductive part of the circuit. Alright. So we know that it's measured in VARs, and that there are several formulas for calculating VARs, and the one that we'll just go with is going to be VAR S equals EL times IL. And so where EL is going to equal voltage, and all this is applied to an inductor. IL is going to equal current flowing through an inductor. And just so we remember what XL means, what does XL mean? It's going to mean inductive reactance. Alright. I know you can't see that, but it means inductive reactance. So, moving on to Q of an inductor. The amount of resistance compared with the inductive reactance determines the quality, also known as Q, of the coil. Inductors that have a ratio of inductive reactance to resistance are considered to be inductors of higher quality. An inductor constructed with a large wire will have low resistance and a higher Q. Inductors with many turns of small wire will have more resistance and lower Q. So, large wire with low resistance, a higher Q. Small wire will have more resistance with a lower Q. And inductors that have a Q of 10 or more are considered to be pure inductors. So remember that. So calculating Q, your formula is going to be Q equals XL over R. So you're just dividing the inductive reactance by the resistance, okay? So we're going to look at this one. We got a resistor right there. And then we've got an inductor right here. So you're going to divide that by your resistance, okay? And another little note is, so if we have an inductor and it's got large wire, alright, it's got large wire, it's going to produce an inductor with a high Q. If we've got small wire, so really small tiny wire, we've got more resistance, so it's going to be a low Q. Okay? So once the ratio of inductive reactance becomes 10 times as great as resistance, the amount of resistance is considered negligible. For example, assume an inductor has an inductive reactance of 100 ohms. So the inductive reactance is going to equal 100 ohms. And a wire resistance of 10 ohms. So we're just going to put R as 10 ohms. Right? The inductive reactive component in the circuit is 90 degrees out of phase with the resistive component. This relationship is going to produce a right triangle. And this is how you're going to see the relationship with inductive reactance and impedance. Okay, so we're about to go over impedance and inductive reactance. So coil impedance is a combination of wire resistance and inductive reactance. So it's got a wire resistance and XL, which we know equals inductive reactance, okay? So that's what impedance of a coil is. Okay, so Pythagorean theorem can be used to calculate the value of impedance. So here is an example. So we've got Z. So Z is going to stand for impedance. Z equals R squared plus XL squared. Alright, so say for example, we're using the fact that we have the 100 ohms of inductive reactance and we have the 10 ohms of the wire resistance. So we know that impedance just equals wire resistance and inductive reactance, right? So all we're going to do is we're going to square that 10 and that 100. And that's going to bring that down to 10,100. Alright. And so our answer is going to be 100.499 ohms. See that? Yep, you can actually see that one. Alright. So now the total impedance for the inductor is only 0.5 ohms greater than the value of inductive reactance. So if it should become necessary that we determine the true inductance of an inductor, the resistance of the wire must be taken into consideration. Alright, so we can find the total current limiting value, which is also impedance, with Ohm's law. So you can use Z equals E over I as well. So if you're given an inductor and it's connected to, I don't want to go too low over here, I'm going to come over here. If you're given an inductor and it has 480 volts, alright, and it is 60 hertz, and it has a current flow of 0.6 amps. And you have used an ohm meter and you found 150 ohms of wire resistance. Okay? So we found all that. Let's see if I have it on the next page. Okay. 150 of wire resistance. So we're going to use this formula up here. So we've got Z equals E over I, so that's just our voltage over our current. So that's going to be Z equals 800 ohms. Okay? So that is just our impedance. So now we can use that to find. So now we have our impedance and we have our wire resistance. We can also find inductive reactance with this. So that formula is going to be, by the way, all these formulas are in your book because I know it's hard to remember. So that formula is going to be Z squared minus R squared, because you can turn these around. So the first original formula I gave you for impedance was Z equals R squared plus XL squared. So we can swap these values around in order to find inductive reactance and impedance. So if we're given inductive reactance and the resistance of a wire, we can find impedance. If we're given the impedance and the resistance of the wire, then we can find inductive reactance. So you would just plug that in. You would just plug in your 800 ohms minus your 150 ohms squared, and that would give you your answer. Alright, so going over a little bit of a summary here. So we know that inductive reactance is the counter voltage that limits the flow of current, as does resistance. Inductive reactance is going to be measured in ohms. Inductive reactance is symbolized by XL. Inductance is measured in henries. So inductance and inductive reactance are different. So inductance equals henries. Whereas inductive reactance, I'll just go ahead and write that up here. Is going to be equal to ohms. Okay? So when inductors are in series, the total inductance is equal to the sum of all the inductors. We talked about that. So that's just going to be series is going to be equal to the total inductance is going to be equal to L1 plus L2 plus L3 and so forth. In parallel, whichever formula you use, you can use product over sum or the reciprocal. I just personally learned the reciprocal, so that's the one that I like. Is going to be LT is going to equal 1 over L1 plus 1 over L2 plus 1 over L3. Alright. All inductors contain some amount of resistance. Okay. Inductors with a Q of 10 or more are generally considered to be pure inductors. So pure inductors are going to equal Q of 10 or more. That's something important to remember. Reactive power is measured in VARs. Power is going to be equal to VARs. And VARs is an abbreviation of volts, amps, reactive. And just to go back over some of the formulas here, just so you don't forget them. So inductive reactance. If you're given inductance, okay, so inductance. So you're looking for inductance. So your inductance is going to be equal to your inductive reactance over 2 pi frequency. Okay, so that's your inductance. Then your impedance formula is R squared plus XL squared. But we also know that can be flip-flopped around, depending on whichever one you're given, right? And your R is standing for wire resistance. Okay? And you can also find impedance with Ohm's law. VARs is going to be equal to EL times IL. Okay, and the last one is, of course you can say it outside. The last one is your inductive reactance. So your inductive reactance is going to be equal to 2 pi FL. So that's just going to stand for 2 times pi times frequency times inductance. So it's just literally the opposite of this one. All right. So that completes that, and I'm going to ask you to do the inductance chapter, the inductance and inductive reactance chapter in your book this week. And we're going to be using some of the tools out here to show inductance. I'm going to make a video about that probably as well on Monday, so that you can just mess around with those and you can understand the concept of inductance and why it's important.